Hi, I'm Gary, and I want to show you how I use Cloudy. So we've been talking about specifying the radiation field striking a cloud. We found there's two parts. There's the shape, which is the SED shape, and then secondly is the brightness striking the cloud. And there's two ways we do that. One was the luminosity case we talked about in the last video. Now we'll talk about the intensity case. So the intensity case is where you specify the intensity of light striking per square centimeter of cloud surface. So that's what Cloudy needs to get rate equations in atomic physics. So you don't need to do a radius. The intensity case will report lines in intensity units, ergs per square centimeter per second. This is the equation for the flux of photons. This is the intensity equivalent of the Q of H command, which is the total number of photons going out into the universe. So the interpretation of phi of H is that it's the actual flux per square centimeter of ionizing radiation coming in, hitting this ionization front. So this is all of these commands are in hazy, and they end with a summary saying their intensity or luminosity case. The second command we saw in the luminosity case was the total luminosity or luminosity command. We have an intensity command, which is the equivalent, but for the intensity case per square centimeter. Like luminosity, the default is for the intensity to be over only hydrogen ionizing radiation, but you can specify it over over any photon range you like by using the range option. So the most common use of this command is if you're looking at a PDR, I'm doing a simulation of a PDR. That literature specifies the radiation field frequently in terms of the galactic background starlight radiation field. Was first done by Having in this classic paper, and some literature refers to the background as the Having field. G naught is a roughly one having field. It's just given this parameter here. So an active star forming region might have G naught of 10,000. So if you go back to the original papers by Thielens and Hollenbach, they defined their version of a G naught, which would be equivalent for us. You'd do intensity in a range from 6 eV to 13.6 eV. Different authors, the famous Drain paper, for instance, have slightly different definitions of this energy range, and they differ still from how Having did it originally. So they're ranges that suit different purposes. So this is a useful way to specify parameters for this literature. There are other ways to set the intensity. If you're thinking about thermodynamic equilibrium, it's very convenient to have in mind the energy density temperature. We take the luminosity or the intensity of light, ergs per square centimeter per second, divide by the speed of light, and then you've got the energy density, so it's ergs per cubic centimeter. And then for the Stefan radiation constant, this equation given right there, you can convert that back into an energy density temperature. So this is very convenient when thinking about uh, the approach of thermodynamic equilibrium. The specific flux can be specified, specific intensity that can be specified at a arbitrary energy. This is the first of our two ionization parameters. It's not one that I use much. It's a parameter you see a lot in the X-ray literature. It's a Zeick parameter. So it was originally defined in this uh, Bruce Tarter paper and redefined once by Krolik. And then the definition we use is the current X-star definition, which is in this paper. So that's the one that's used in the X-ray community. So what they're adjusting here is this range option. They're 1 Rydberg up to 1,000 Rydbergs. Rydberg is the hydrogen ionization potential. So you can use that if you like it, but the one that I use mostly is the dimensionless ionization parameter, which is roughly equal to of order the ratio of the radiation to gas pressures. And so this ionization parameter U is defined as the ratio of the the ionizing photon density to the hydrogen density. So it's dimensionless. So you take the flux of photons. So this is Q of H, the total number of photons emitted into the universe per second. You divide by 4 pi r squared, the distance to the cloud. This turns this ratio into flux, the flux of ionizing photon is phi of h. So this is photons per square centimeter per second. You divide by the speed of light, that becomes photons per cubic centimeter. You divide that by the hydrogen density, that's also per cubic centimeter, so this is dimensionless. This is a frequently used parameter. It's very useful because it's proportional to the ionization of the gas. So these are some equations. The first one is from Osterbrock, chapter 2, and it's the ionization balance equation for hydrogen. It just says that the atomic hydrogen density times the integral of the number of ionizing photons at a particular frequency times the photoionization cross-section at that frequency. This entire integral is the photoionization rate, which has units per second. So this is the rate hydrogen atoms are destroyed. This is the rate they recombine. This is proton density, electron density. This is a recombination coefficient, which only has atomic physics that describes the details of how it recombines. So this is the ionization balance equation for hydrogen. You can rewrite it a couple of steps here, and you can end up solving for the proton to atom ratio, the ionization ratio, is these parameters, which is proportional to U. So frequently, if you vary different parameters and you see the ionization of the gas changing, if you trace it all the way down, what's really causing that? Probably what's causing it is the ionization parameter is changing. So it's pretty fundamental. And we'll come back in the next video. What we're going to do is set up a simple sim where we vary the ionization parameter in a grid command and do a series of clouds with varying ionization parameters. And we'll see what that does to the ionization of the cloud and then also its temperature. So that's in next time, and I'll see you then.